So it's a pleasure to be here, and in a way it's a great honor to be after my good friend David. We go back since 1962, I think. Yes, we are probably more or less what is left of the originators of the joint seminar. Now, this is not necessary. To the younger people here, it is perhaps not clear what is the November Revolution. The November Revolution started on November 11. What happened on November 11? Everybody who has been in Europe knows that November 11 is called Armistice Days or Veterans Days or Memorial Day. It's the end of World War I. That is not the subject today. We are talking about November 11, 1974. What happened in November 11, 1974? If you go to Google, you find that Leonardo was born on that day. Not Leonardo da Vinci, Leonardo DiCaprio. That's also not the subject. But on November 11, which means 11/11/74, at 11 o'clock in the morning California time, there was one of perhaps the most dramatic physics event that I lived through personally, and perhaps the most important single event in experimental physics in the last, I would say, definitely 50 years, probably even more. It was a Monday, and I was on sabbatical. And now perhaps let's move back to the joint seminar. The joint seminar was then 7-year-old. It started by our group of young people coming back from the postdoc. And we were all in university positions as professors or senior lecturers or whatever. And after 7 years, what does a university professor do? He goes on sabbatical. So I was lucky enough to go on sabbatical on that year to Stanford, and to wake up on Monday morning, November 11, 1974, and go to work as usual, to find out that at 10 o'clock in the morning, a seminar was announced for 11 o'clock in the morning. It was not planned before. A double header, like this session here, 2 lectures back to back, and that was the beginning, and that is the subject that I will refer to, but in a broader framework. So the broader framework that I want to talk about is basically wonderful. Okay. It's the 20 years from 1960 to 1980, and I want to very quickly go through what happened in physics, faster than tweeting, what happened in Israeli particle physics at that time, the tools that we were using, and a few personal comments about what happened to me. So we start with, and with an emphasis on the November Revolution, what led to it, and what happened after it. So we start with 1960, 61, 62. Physics has 3 leptons, neutrino, electron, muon, only 1 neutrino, approximately 50 hadrons in 60 or 61, multiplying again and again. Every week, every 2 weeks, another hadron is being discovered, another resonance. By 63, 64, we had almost 100. In Israel, Yuval Ne'eman finished his PhD in Imperial College. He was the first Israeli to do a theoretical particle physics PhD. Came back to Israel. He became the director of a lab of the Atomic Energy Commission, and his condition was that he will be allowed half of the time to direct the lab and half of the time to do particle physics. He succeeded in exciting Tzvi Lipkin, who was here, who was already an experienced and many achievement nuclear physicist and other fields of physics, and that was the beginning. The tools were, first of all, in the 60s, the Weizmann original computer of the Weizmann Institute. Those of you who haven't seen it, it's still on display in the entrance of the math building. It's really fantastic to look at it. Joe Dotan and I came to do a master's thesis here, and we were in a little room on the roof. Now there's a whole empire on the roof of this building. We had a room of 2.5 meters by 1.5 meter for the two of us. And one thing, perhaps you can help me, there was no Xerox machine, no photocopy machine anywhere. It was not yet invented. And I have no idea what we did when we went to the library and saw an article that we wanted to read peacefully in the office or at home. I have absolutely no memory of what happened. So if anybody remembers, please come to me after the lecture. But it's very hard. Everything else I remember what we did without smartphones and without long-distance phone and without computers, but I don't remember what we did without a copying machine. Then came the first group of students, what is written here under Israel as Students 1. Student 1s were all the names that David mentioned: David Horn, Joe Dotan, Moshe Kugler, Shmuel Nusinov, Arnon Dar, myself, others, and unfortunately some of them are not with us anymore. Next time celebrate the 40th anniversary, not the 50th. That's a lesson that I learned in life from other places. In the meantime, Gelman and Zweig proposed the quarks in 63. CP was violated, or known to be violated, in 64. It was violated after the Big Bang, otherwise we wouldn't be here. But it was known to be violated in 64. The second neutrino was found. And charm was proposed by Glashow and Bjorken on the basis of why not. They say we have already 3 flavors. They were not called flavors at that time. Why not 4? Why not 5? Why not 6? So they said, why not 4? That was, everybody refers to Glashow and Bjorken, but it was independently done by a Japanese named Yasuo Hara. And Glashow came to visit us and give a seminar here at this building at the Weizmann Institute, and he knew my name because I wrote a few papers already as a graduate student. And he was sure that if Hara is Japanese, Harari is also Japanese. And I was introduced to him by Lipkin, and he looked at me and said, "Oh, I thought you were Japanese." So he learned. Okay. And that was it. Meanwhile, I got my PhD. And we move on. And the whole group of students who were mostly working on symmetries, David with weak interaction, others with strong interaction. There was very little crosstalk between the strong and the weak interaction and the electromagnetic. These were almost 3 different fields of physics. And then came the 2 years of the postdocs. David referred to it as the Israeli mafia. IL mafia does not mean Il mafia, it means IL for Israel. Actually, there were 3 mafias floating in theoretical particle physics, and it was very interesting because it created a community for generations. There was the Firenze mafia of Veneziano, Ademolo, Altarelli, Maiani, who later was the director of CERN, and several others. There was a Princeton mafia of that generation: Adler, Weisberger, Fred Gilman, Bob Sugar, and other people, Kurt Kallan. And then there was the Israeli mafia of the postdocs, the names that you mentioned. And each of these mafia was a group of 5 or 6 good scientists spread in the best places in the United States or in Europe. And in every place there was one from each mafia. So without email and without all the ways of communicating today, we were all networked in a very good way and remained so for decades after that. Meanwhile, Zvi Lipkin, who was here, started a whole business of quark counting. The quark model was proposed, quarks were not found, there was no evidence, there was vaguely a hint, there was no evidence for any substructure inside hadrons. But Zvi, in a typical way, he said, forget all of this problem, let's assume that they exist. And let's see what we can learn from that. And he wrote some remarkable papers that didn't make any sense because there was no real evidence for quarks, but many of the results that were driven were correct, surprisingly, and were also understood 5 years later when the subject progresses. Meanwhile, David and Christoph Schmidt at Caltech and later Schmidt at Zurich introduced the finite energy sum rules, which David talked about. We were using airmail under tools, you will see. We were using airmails. There was very rare long-distance phone calls. So we basically were always a week away from the news in the best possible situation, but we tried, all of us who were spread around the world, were trying to keep the guys at home completely up to date. And then a few very interesting things happened after that when we came back. First of all, the joint seminar, which you have in red under tools, started because we felt isolated here. The nearest physics was in Italy, and not much was going on there, and it was 3-hour flight and 1 week by airmail. And our way to survive was to communicate with each other every week. Under tools, you see the view graph. That historic archaeological instrument which we were using. At that time, it only began to be used in particle physics, and later there was the whole art of using overlays to make a point and comparing theory and experiments and all sorts of things like that, which was a great innovation. I, more than succeeded in physics, succeeded in this hocus pocus in many conferences, and this was a passion. I will show you an example or two in a minute. That's why it's there. And in the meantime, the whole idea of finite energy sum rule of David Horn and Chris Schmidt was being developed. There was this recognition that the only regipole which does not fit into the picture is the Pomeron. There were the duality diagrams which you heard about, and another group which was not one of the original group of Rubinstein, Veneziano, and Virasoro started working here on other issues related to the above, which eventually led to the Veneziano formula, and they were laying the foundation of this in papers written by all three of them. So just to repeat, but in a very unprofessional language, what David was saying, when a meson met a baryon, one possibility was that they would unite to make a higher baryon, this picture that you see here, which then would split. Another possibility is that they would exchange a meson and create the same final state. And the duality diagram story was to simply draw the same picture in terms of the quarks composing the baryons and mesons. Now I want to answer the question that was asked at the end to David. You have to understand, first of all, their idea was ingenious because it was totally crazy. I mean, we were all brought up from field theory, from QED, to understand that these two diagrams at the top of these slides are different. You have to take one of them and the other and add them up. That's how we learned in school. In kindergarten, we learned it. And then these guys say, no, you take only the first one and sum it over all, and that's the end of the story. Or you take the second one and sum over all, and that's the end of the story, and the result is going to be the same. And if you do both, you simply got twice the result. You count twice. I mean, this is so crazy when you take a idea fix and break it, and that's why it was so clever. And it was hard to argue with it because it was correct. It's always hard to argue with the correct. But at the same time, the quarks were not understood at all. Nobody believed it. Most people didn't believe in them. They were looked for. And then suddenly, the duality diagram, which is a childish discovery, it's not even a discovery, it's a childish cartoon, was to take these two processes, which are very different, and to draw them in terms of quarks. And you see that there's only one process here. And Today, in retrospect, this whole thing is not very relevant, but this was a very important step to unite the dynamics of the strong interactions and the existence of the quarks, and to see that these two ununderstood puzzles talk to each other, and that was the importance of it. So that's where we were. And now, allow me to introduce to those of you who are under 30, if there is anybody like this here. This is a slide which I found at home 2 days ago from '68. And you see, it always say all generals never die, they just fade away. The same is true for viewgraph transparency. This was lying in my basement since the late 60s. You see all of these stories that are written there, but what is much more interesting is the other slide which I found, which is 2 years later. And there the question was, okay, brilliant. So you describe it in terms of quarks, but where are the quarks? How come we don't find quarks? This is before QCD, before confinement, before we knew anything about, and before deep inelastic scattering, showing that there are point-like objects inside hadrons. So here is what we used to say about it in '69. Look, what I wrote here in a seminar in '69. A magnet has 2 poles. There is no monopole. But there is a pole of a magnet, but only as part of the magnet. A wire, I didn't call it a string, it was called a wire. A wire, every wire has 2 ends. So there is such a thing as the end of the wire. But you cannot have an end of the wire and discover an end of the wire without the wire. A wire with 2 ends can split into 2 wires, each of which have 2 ends. That's a meson splitting into 2 mesons, each of which has a quark at one end and an anti-quark. So that's the first time that the thought of a string appears, not me. I mean, I was broadcasting common wisdom. It's not something I discovered or anything, but I just found the slide. But this is, of course, nothing to do with string theory, because that is the quark here. The whole point here is that the quark is point-like, and the meson and only the meson is the wire. So there is no implication here that every point-like object may or may not be a string. It's just a very childish concept, or whatever you want to call it. But it was some kind of a beginning of thinking about those things, and soon after came, and here you see, at the bottom right, you see again that same thing, and this is also, this is of course, since it's PowerPoint, this is about 15 years old, this particular slide, and it says meson is a wire, it can split into 2. Okay, back to the history. It says on the left, Princeton. That's a very interesting thing about the development of particle physics in Israel. In Princeton, in '68, '9, there was a decision to collect all the top guys in the field in the world to one place, and they will solve all the problems. Gell-Mann was there, the whole team from MIT, Goldberger and Lowe, and all sorts of people were there. It so happens that all the wisdom in that year came from Tel Aviv and Rehovot. It was just amazing. I mean, you've heard already about the finite energy sum rule, the duality diagrams. There were a few other things. I don't want to go one after the other, and eventually the Veneziano formula. It was just amazing. The bunch of young people here who were halfway reasonably known, but not much more than that, it was incredible. In the meantime, deep inelastic scattering at SLAC showed the point-like structure. And then came Veneziano, and it became more and more clear that the hundreds of hadrons fit exactly the pattern of the spectroscopy that the quarks demand. You go up a few lines and you see the word electroweak. Steve Weinberg, in 1967, proposed his theory of the weak interaction. It was said before that nobody paid attention to it, including Steve Weinberg. In 1968, Weinberg was the rapporteur giving the summary talk of weak interaction in the big international conference in Vienna in the palace of Franz Joseph, the emperor. 800 people heard Steve Weinberg summing everything that happened in weak interaction in that year. He didn't mention his own work about SU2 cross U1. You can go back to the proceedings and check. He didn't think his own work on SU2 cross U1, which later gave him the Nobel Prize, was worth mentioning in the summary of what happened in the last 2 years. Instead, he devoted 1/4 to a paper by Fred Gilman and myself that both of us barely remember what was even written there. It was so important. So, I mean, the history of these things is amazing when you start digging into it. And then came the second generation of students, the students of our group, and the later students of Yuval and Zvi, many of whom are sitting here, Eliezer and Shimon here, and Michael Gronau, and others are sitting, Yoav. And it started a whole tradition, Moti Milgrom. I'm sure I forget somebody, but a great group of people that continue the school. We finally had remote terminals, computer terminals, not PCs, but remote computer terminals. Computers crept into administration, doesn't matter. I became dean of the graduate school, which is not relevant to anything here. And then charm was predicted most seriously by Glashow, Iliopoulos, and Mayani. And I think one of the most criminal acts of the Nobel Committee is that they didn't give the Nobel Prize for that, because that's really one of the all-time great papers in the history of particle physics. They explain not that charm may exist, but that charm must exist, and that there is a solution, and nobody believed them, and nobody paid attention to it, and almost nobody worked on it. And soon after, and that's going to be important in 5 minutes when I approach the end, there was a second, not only the renormalization proof of the electroweak model of Weinberg and others, but there was something else which became a little footnote, and maybe some of the younger people here don't even know it. And I don't know how that it was important and not understood. There was this famous triangular anomaly that was also needed to vanish in order for the electroweak theory to be renormalizable. And the only way it could vanish was if the sum of the electric charges of all the quarks and all the leptons would be 0. And that was extremely crucial, because that was a purely theoretical indication for color, and it was a purely theoretical indication for a charm quark from somewhere which is totally unexpected. And we'll come back to it in a minute. In the meantime, neutral currents were found. Kobayashi Moskawa wrote a paper about CP, but if you read the paper of Kobayashi Moskawa, which nobody paid attention at that time, it was published in the Japanese journal, the paper is not at all about what is called now the KM matrix. It was about another model which is wrong. There is an appendix which says that if the model is not correct, there is another possibility of having 6 quarks. And that's a very short footnote, and that's not what they meant to, and that's why the paper remained totally unread anywhere outside of their milieu for 2.5 years. And then came the November revolution, 11/11 at 11 in the morning, and the psi particle was discovered simultaneously at SLAC and at Brookhaven by Richter and company and by Ting and company. Now I'm giving you homework, and please take it and do it after the lecture. If you are bored, you can do it now here if you have a laptop or a telephone. I'm not encouraging you to do it now, do it later. Go to Google Maps type Paris, Paris, France. Make sure it's Paris, France, because it's probably Paris, Texas or something. When you get Paris, France, go not to the map, but to the satellite pictures. Find the Eiffel Tower, the Tour Eiffel. You will see the words Tour Eiffel or Eiffel Tower, and start zooming in slowly, 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 slowly zooming in. You see nothing. And suddenly, you have this spike that hits you in the eye, and just try it. I mean, it's really an impressive exercise. What does that have to do with the November Revolution? That's exactly what happened. SLAC was measuring the total cross-section of electron-positron annihilation. They had a graph which was, I can draw it. Is there still chalk in this place? They had a graph which was like this. And on that weekend of November 9, 10, they found some points in the middle, and they found that the interpolation is this. Just like Tour Eiffel in Paris. And that was the big shocker, and eventually this was the discovery of charm, and that led to everything else. Now, that happened in a weekend, and I sent a letter to Rehovot, airmail, and that's why I have it. I still have the letter. Friday, November 8, 1974, to Tzvi Lipkin. In English, because we were corresponding with Tzvi in English. Dear Tzvi, we are now settled. We just arrived 2 months ago. We are now settled in Palo Alto. Life is quiet and quite boring here. All the action is in Fermilab. It's hard to see that something exciting will come up. The SPEAR machine, that's the electron-positron collider, started working, and we hope for the best. November 8, Friday, November 8, 74. Monday morning, that's how it began. But in the following 9 months, which is really exact pregnancy, things were getting murkier and more complicated. Everybody at the beginning said this must be charm. Then there was a list of 5 experimental predictions. I don't have time to go through them. There has to be excited states of the psi. There have to be a certain value of the total cross-section. There has to be preponderance of strange particles. There has to be this and that. There were 5 predictions. All of them were wrong experimentally. All of them, not one wrong. Meanwhile, somebody else at the same group, at the same experiment, was discovering another particle which nobody else in the group believed him. That was Marty Pearl. And I was there together with B.J. Bjorken and Frank Gilmal trying to make sense out of the whole thing from the phenomenological point of view. And failing and failing and failing, because it more and more looked like charm, and charm looked more and more wrong. And there was no way to understand what was happening. And on the side, like a sideshow, like the warm-up singer for the main show, there was Marty Pearl with these strange events that he was finding that nobody believed. And there were 9 months of false starts. I proposed the existence of the top and bottom quarks and gave them their names because I thought that would explain why there are no excited states of the psi. 2 months later, the excited states of the psi were found. So my prediction of the top and bottom was without foundation. But I said that if the top and bottom quarks exist, there should also be 6 leptons. Because you remember I told you that there is a triangular anomaly, and the sum of the electric charges of all the quarks and all the leptons have to be 0. And if in addition to charm there is top and bottom, then in addition to electron and mu, there has to be something else. But since nobody believed Marty Pearl at that time, that was, I invent top and bottom, and therefore there has to be additional leptons. And it went on and on and on and on ad nausea. And the story of those 9 months, I mean, if you think about a pregnancy, and somebody, excuse me my crazy analogy, and somebody describes a pregnant lady describes every single morning that she vomited. That's what we had for 9 months with charm, because we were getting sick by the whole thing. I mean, it was more and more clear that it's charm. There was no evidence. Meanwhile, we have other discoveries there, and this is always neglected by history. That same experiment was the first time that the charges of the quarks were pinned down by the total cross-section of E plus E minus interaction, and the first time that quark jets were seen, indicating that what is formed is a quark, which then dresses up by mesons. And these are two very remarkable discoveries, but because they were made by the same group the same year, they remain in the background. And then in August 75 came the big lepton-photon conference at SLAC. And here I'm getting very personal, because I had the honor of giving the rapporteur talk of covering all the theoretical development, the theoretical interpretation of everything that happened. And I had no idea when I prepared the transparencies of the view graph, I had no idea what to say, except to say everything points to charm, and charm is completely wrong. And it was only that morning, literally the morning of the beginning of the conference, not the morning of my lecture, one day before, that it's like a lightning. I understood that what Marty Pearl did and nobody believed was a new lepton. My top and bottom were wrong. Therefore, we have charm and a new lepton tau. They appear surprisingly, accidentally, without any reason, at the same energy. And therefore, all the properties that we think are property of charm are really a property of a mixed half charm and half tau. And charm and tau had opposite property. One has more strange particles and tau has less strange. One had more neutral decay modes, the other had less decay modes. All the properties were such that when you combine the two samples, it looked like nothing happens. And I remember that in the talk, I referred to an old story that in Rome, archaeologists found a little wire, and they concluded that the ancient Romans were using telephones. And in Jerusalem, the archaeologists didn't find anything, and they concluded that the ancient Israelis were using smartphones. And that was essentially what happened, because we were looking at the data to look for charm, and we found nothing, and I was claiming, therefore there is charm and tau, and that's why we find nothing. And that happens to be correct. And then, if you have tau, you have 6 leptons. And remember the anomaly diagram. If there is 6 leptons, there have to be 6 quarks. So my top and bottom were correct, but not where I wanted them, but at much higher energy that was not yet available at SLAC. And here is the punchline from that talk. It says, after going through possibilities that don't work, I read it loud: one new quark, and 2 new leptons. The tau, they so much didn't believe it that they call it U for unknown. So it's unknown, and the neutrino of the unknown agrees with all known data, does not possess quark lepton, but it does not possess quark lepton symmetry, and the anomalies are not cancelled. We see that at present, this D seems to be the only viable scheme from the experimental point of view. Theoretically, however, we prefer to supplement the 6 quarks, nu E, as a 6 lepton, nu E, nu mu, nu U, and E, mu, U, with 6 quarks within a V minus A theory. This must be up and down, charm and strange, top and bottom, where top and bottom have electric charges plus 2/3, minus 1/3 respectively. The T and B quarks are presumably produced at energies above 8 GeV, or else we would have already seen the TT bar and or BB bar vector mesons. Now, that is the first time ever that the 6 quark 6 lepton scheme appears anywhere. And that's basically the last bit of the list of particles that we have today. All the others were predicted before. That does not mean that we found them, but I just want to show you transparency just to see the progress of technology. I also found that thing in a transparency from the old days. You see how wonderful, readable, clear. It's the same. I just show it for the sake of comparing technologies. In any case, that was the story at that time. There was a lot of work. I mean, this is just a highlight. There was a lot of work done both there and here by many of the members of our groups here. And all the information was flowing fantastically. And then came the confirmation. The tau was confirmed. The D meson was found. The big quark, the gluon. And then the question was, what is beyond the standard model? And here we are more or less where we were before. Y3 generations. I proposed the sub-quark, sub-lepton model called the Rishon model, which nobody works on and nobody believes, but of course there can never be an evidence against a subparticle model. And I must say, for the record, I still believe that there is substructure, and the substructure must be more or less along these lines. And the up quark, as you see at the bottom line, consists from TTV. That paper was written in the middle of '79. If you read TTV in Hebrew from right to left, you see Vav Taf Taf. And at the end of that year, I came to Israel, and I was faced with becoming the chairman of Vav Taf Taf, Vatat. And the coincidence between the TTV of the Rishons and the Vatat is one I should have bought some lottery or something. And that's basically the story. Here is the reason why I firmly believe that there is something behind the particles. That's the last story. You see the leptons on the left, the quarks on the right. These are the electric charges. It's the only thing we show. Now they're all together. The lepton and quarks are on the left. Now there are the antiparticles. Now all the antiparticles and the particles. And when you look at that and you see that everything from 1 to -1 at jumping 1/3 exists, and you see that nothing above 1 or below -1 exists, and you see that all the yellow ones are the quarks and they appear 3 times for 3 colors, and all the orange ones appear once, and the ones that appear once is integer and the others are not, then you simply cannot escape the conclusion that there is some mysterious hand which is arranging this from one building block with charge and one without charge. How? It is now almost 40 years and we don't know. We have no idea. It must require some new wisdom. That's why nobody is working on it, and that's why it's really but meanwhile, the W was found, the Z was found, the top was found, the B was found, the third neutrino, the Higgs, and we remain with a list of open questions, which is more or less the same list as before. The only new ones relate to dark matter and dark energy. And that's where we were 40 years ago. That's where we are now, more or less, in the phenomenology. And there is great progress in other things, but I'm very sorry that we remain in such a situation. And that concludes the story, which I could spend 5 hours telling, but I tried to overrun my time only by 50%. Thank you. Absolutely. Absolutely. And I learned, I personally had two opportunities to learn how by making a catchphrase you get into headlines in newspapers. When the gluon was discovered, it was first reported in the big international conference in Fermilab in '79. And I was the rapporteur who discussed the theory side of it. And then there was a meeting of the DAISY people, experimentalists, and I, and the organizer of conference with the journalists, the science journalists of the Chicago Tribune. And the DAISY people explained what they did, which is the important thing. The journalists didn't pay any attention. And I said, because they declared the discovery of 3 jets in E plus E minus collision. That was really the discovery. And I said, 10 years from now, when we look back, we will say that the gluon was discovered in the summer of 1979 and reported first in the Fermilab conference by DAISY. The following day, Chicago Tribune, Chicago Sun-Times. That was the headline, as if I did anything about it. I mean, it's so idiotic. And after the Psi, on that conference, the Palo Alto Times interviewed Sam Ting, who said charm will never be found. So I said to him in front of the journalist, I bet you $10 that 2 years from now charm will be found. And this appeared as the main headline of the Palo Alto Times. And 2 years later, I met him on the same day at the CERN cafeteria. And before he said hello, before we shook hands, he took $10 and gave it to me. I said, no, Sam, I want a check. He said, no, if you get a check, you will not deposit it in the bank, you will hang it in your office. That's why I give you cash. So, I mean, there are about 1,000 stories like this. Yeah, but I mentioned the gluon, but I mean, there were so many things happening in those years. Okay.
Okay, let's thank